Today we'll continue where we left off yesterday, which is a general statement of the first order conditions for incentive compatibility. So here we allow n agents. So we make some assumptions on the agents' utilities and on the stochastic process, and also assume independence of this processes across agents, conditional on the decisions of the mechanism. And then the conclusion is in any Bayesian Nash incentive compatible choice rule, each agent's equilibrium expected utility as a well, this is in the initial period as a function of the initial type, has to be Lipschitz continuous in the type, and its derivative has to be given by this formula. So this is kind of the key formula. I want you to keep it in mind, so I tried to copy it on the blackboard, but there's not much room there. I omitted all the arguments, but the intuition is very simple for this formula. Just think of it as a chain rule. So if there were no maximization by the agents, if this was kind of a constant mechanism, this would just be the chain rule, okay, where you calculate the derivative with respect to the initial type by calculating, thinking of that all the future types are functions of the initial type. Okay, so the derivative of the utility with respect to each of the future types multiplied by the impulse response, which is the derivative of the future type with respect to the initial type, holding the independent shocks fixed. Okay, so you multiply them, you add them up over time, and you take expectation, and you get your formula. Now, of course, the static case would just be where only the initial term matters, and the convention, the impulse response of the initial type on itself is 1. So then this would be just 1, and this would just be the partial derivative. And here, in the dynamic case, you have to add up all those terms. And this is a formula for the impulse responses, and we had, well, that sort of says what I said in words in the formula, and then you can derive it. If you have an independent shock representation, you can derive it, or you can derive it using the canonical representation from by differentiating the CDFs as I showed you last time. Okay, so now we have this formula. This is necessary conditions for incentive compatibility, and the next step is I want to show you how it can be applied, and you will see applications of this to dynamic taxation pretty soon. So I will show you a different class of applications, which is applications to profit maximization with participation constraints. And you would say maybe profit maximization is not a good objective for public economics. On the other hand, if you think about a situation where you want to provide a public good, for example, maybe you care about welfare, but the public good has some fixed costs. So you need to cover the fixed costs, so you have some revenue target. And then basically maximizing expected welfare subject to some constraint on expected profits will give you a very similar problem to just the problem of maximizing expected profits. You'll just put, well, yeah, or you just put some weight, in other words, a Lagrangian, some weight on profits and some weight on welfare, and qualitatively it will be very similar. So that's our application. Okay, so now we want to write the participation constraints of the agents as well. So maybe agents can quit the mechanism in the beginning. They might also be able to quit the mechanism in every period, not just in the beginning. So that would make a very complicated problem, but the simplest case to solve for us, that's the one we focus on, would be the one where there's no payment constraints. So you can always ask the agents to post a very large bond in the beginning, and that will be only repaid eventually in the future. So that eliminates the temptation to run away in the middle. Okay, so that way you can say you can relax all the participation constraints except for the initial ones. Now, of course, it's not always realistic, and I think we should study more applications where agents have some payment constraints or consumption smoothing, for that matter, that will prevent this kind of bonding, but will make it into a harder problem. Okay, so for now, we just look at the initial participation constraints, so that they just say that the expected utility for all the types is non-negative, just normalizing the reservation utility to 0. So we'll now look at the relaxed program, where we instead of all the incentive constraints, we only use these first order conditions. And instead of the participation constraints, we'll just look at the initial participation constraints only of the lowest initial types. Okay, and then as usual, then there will be some assumptions under which once you satisfy the participation constraints of the lowest types, all the other constraints will be satisfied. And also there will be sufficient conditions for this first order ICFOC conditions to imply all the incentive compatibility constraints. So that will be what we'll talk about later. But first, let's just understand the relaxed program. And now the usual trick to solving these problems in the static setting, and we'll do the same thing here, is to calculate, so use ICFOC, use this expression for the derivative of the agent's utility to calculate the expected information length of the agent using integration by parts. Okay, so this is the usual trick. I just copied it here. If you remember it, you don't need to read it, but if you don't remember it, so the idea is that you can calculate the expectation is just the integral using the CDF, the probability measure, over the initial types. Now we do apply integration by parts to it, so we get two terms. The first term is just the change of V times the CDF between the two integration limits. And the second term is minus the integral. Now you differentiate the utility, and you leave the CDF here. Okay, now when you look at the change of this between the integration limits, of course the CDF at the lower limit is 0, CDF at the upper limit is 1. So you just get the utility of the highest type, but you can also write it out as the utility of the lowest type plus the integral of the derivative. And the second term, okay, I just rewrote it here. And the final step is just to bring everything. By the way, the utility of the lowest type we set it to 0 because this is the lowest participation constraint of the participation constraint of the lowest type, and this is the only one that we left, so it will bind. So you can just set it to 0, and you put all of the integrals together, so you get so what you get, you can write this as an expectation of something, and so this will be an expectation of something called the inverse hazard rate of the distribution times the derivative of the agent's utility. So what is the hazard rate of the distribution? Eta, we use eta to denote it, of the distribution at type theta is defined as the density divided by 1 minus the CDF of the distribution. Okay, so that's of course an important measure in static mechanism design. It sort of tells you how many types are above this type versus how many types. So 1 minus capital F is, of course, how many types are higher than theta, and f of theta in some sense how many types theta there are. And it will tell you sort of how much you want to distort type theta, because the trade-off, of course, if you distort type theta more, it allows, of course, it reduces the efficiency on type theta, but it also reduces the information range of types higher than theta. So that's why it's an important parameter here. So here we have the inverse hazard rate. So this argument is completely the same as in the static model. There's nothing new here. Of course, what will be new is you will plug in the formula for the derivative of the agent's expected utility, because now it will be given by this first order condition. So that will be, this is the new part. Okay, so now let's also add the principal, call him agent 0. He might have his own utility function. So the principal could be an auctioneer, for example, have some cost of giving up the objects. And you can express the expected profits of the principal, that's a useful accounting trick, as the difference between the total expected surplus and the total expected information rents of the agents. Okay, so here, this is the formula. So you have the expected total surplus, this is just the sum of everybody's utilities, including the principal, minus the expected information rents of the agents. This is exactly what we did on the previous slide, which is calculate the expected information of the rents of the agents. We add them up. So you plug in the formula for the derivative of the agent's utility from ICFOC. This is the same formula. Okay, you multiply by the inverse hazard rates of the initial types. You add over the agents. Okay. So you maximize the expectation of this. And so your allocation rule has to maximize this expectation. So when you think about it in general, it's a dynamic stochastic programming problem. It could be in general a very hard problem to solve. Of course, in some interesting cases, applications, we can solve it. And what's also interesting is that the difference between this and the efficiency problem. If you just cared about expected total surplus, you would just look at the first term. Okay, now what is interesting to us is how the second term changes the solution. So it introduces distortions. So the principle creates distortions to reduce the information rents of the agents. Okay, and and now what you will see, what is new about, of course, this was also true in the dynamic setting. What's new in the, this is also true in the static setting. What's new in the dynamic setting is that you have these impulse responses coming in. And so you will see that the distortions will be driven not only by the properties of the utility functions, but also by the properties of the impulse responses. So the stochastic process will determine the impulse responses, and they will drive the distortions and the dynamics of the distortions. And so that sort of allows us, there's several, of course, ours is not the only paper that uses this kind of approach, but because we kind of do it more generally, we can sort of unify a little bit and understand how the previous results depended on the various assumptions. Okay, so let's just have a very simple example just to kind of understand the role of impulse responses there. So we make everything time separable so that there's just one agent, agent 1, and the principal is agent 0. So effectively 2 agents. One agent with private information. Okay, so the agent has a time separable linear utility. And A is just a constant that we put here because we just wanted to avoid corner solutions. And the principal has a quadratic utility. So this is quadratic cost, so it's negative. So the agent has linear utility for the good. There's one good, continuous good, and the principal has a quadratic cost of producing this good. Okay, and the stochastic process we assume to be Markov and autonomous. And what autonomous means is not dependent on decisions, so to make it simple. So the agent's value does not depend on how much he consumes, but it's just a Markov process. Okay, so then efficiency is very easy to calculate here because it's just, of course, it separates over time, and you just, in every time period, you just maximize total surplus, and you get this A plus theta t. And we make assumptions that just to make sure that there are no corner solutions, that, well, at least there's no corner at the top. We make assumption that the highest quantity is high enough. Okay, now what about the relaxed program? So this is the relaxed profit maximization program. So the difference from efficiency is effectively you are reducing the agent's utility function. So you're reducing his value down to his virtual value. Okay, and the virtual value is obtained by subtracting this term from his true value. Okay, and what is this term? Just the impulse response divided by the hazard rate of the initial distribution. And what is the impulse response? So one way to calculate the impulse response is, remember, from the canonical representation using the CDFs of the transitions. This is basically what the Baran-Besson coinformativeness index is, just a simple version of this, which is just one period. And in general, you have to compound this over all possible chains of causation. But if you have a Markov process, then there's only one chain of causation, right? Because in the Markov process, theta 0 only affects theta 1 directly, but then theta 1 affects theta 2 directly, and so on. So you just multiply, there's just one chain, so you just multiply all these effects to get the total impulse response. Okay, so well, this here, this is the effect on the utility, plus theta, yeah, okay. So this is the difference. So this is the information rent effect. The derivative utility with respect to theta is simply x here, right? So that's okay. So basically, this term, when you look at this term, this is the derivative of utility with respect to theta is simply x. So in this particular case, so you can think of this term as sort of what you are subtracting from the value. Okay, so the utility, the utility is, let's say in the linear case, theta it times xit. But here, you instead of theta it, you subtract the information rents to get the virtual utility of the agent, which will be theta it minus, this times xit. Okay, so instead of a plus theta t, you get a plus theta t minus this. So this is this. This gives us the virtual value of the agent. Okay, which is again, very similar to the static case, except for this. So in the static case, instead of the I would just be 1, and you would just get the usual static virtual value, which you use in auctions, for example. But here it's a virtual value has this impulse response term in it. Okay. Of course, so the intuition of this impulse response, so the distortions in period t are determined by how much the type in period t responds to the type in period 1. So for example, if the type in period t is completely independent of the initial type, there is no reason to create distortions in period t. Right? So this is sort of a situation, for example, if you can contract with the agent before he gets any private information, so in this world, you will just have efficiency because you will be able to extract his information rent completely. There will be no information rent. So the information rent, in some sense, is still only attributable to his initial private information. So, and the reason you create distortions based on future private information is only to the extent that it is linked to the initial private information. And the impulse responses is what exactly captures the link from the initial to the future. If there's no link, then you don't create distortions. Okay, so that's a kind of straightforward intuition, right? Okay, so now, one thing you see is that the downward distortions here arise, so as long as the impulse responses are positive. Okay. So what does it mean for the impulse response to be positive? That turns out to mean, if you look at this formula for the impulse responses, that means that the CDF in one period is decreasing in the type of the previous period. And this is, of course, a familiar first-order stochastic dominance condition, right? So that means, the CDF being decreasing means that the distribution shifts higher in the first-order stochastic dominance. Okay? So what this means is that simply that higher type today increases type tomorrow in the sense of first-order stochastic dominance. And this is what gives us positive impulse responses. And positive impulse responses create, in this simple example, downward distortions. You want to reduce consumption. So, by the way, so there are various examples where this happens. Corti and Lee also in their paper on advanced ticket sales also built some examples where you don't have first-order stochastic dominance and you have upward distortions. So if you think about what are the distortions in the refundability of tickets, so you would say that some tickets are non-refundable. And that means that, if you bought a ticket, you thought you would have a high value, but there's some uncertainty, and then you got sick, but you cannot refund your ticket, so maybe you will still fly, even if your value is very low, and that's an inefficiency, right? Because presumably your value could be lower than the cost, and you would still fly, and this is actually an upward distortion. So you are consuming more than what is efficient. So the question is, why would it be optimal for the airline to sell these kinds of non-refundable tickets which create upward distortions? Okay, and so the answer of Corti and Lee is that, well, first they look at the case of first-order stochastic domain and say, well, in that case, it cannot happen because you can only have downward distortions. But then they look at another case which they call like second-order stochastic domains, where there are two types: the business and the business travelers and the leisure travelers. And business travelers not necessarily have higher value for flying, but they have higher uncertainty about where they're, about their value, right? So you would think for business travelers, the uncertainty could be that, maybe your meeting will be very important, but maybe maybe you will not have an important meeting, but you will have some other important meeting at home, so the cost of flying would be very high to you. Okay, so and in that kind of model where it's a shift instead of first-order stochastic shift, it's like a second-order stochastic spread, it's like a mean-preserving spread or something like that. Then they show that the optimal mechanism might introduce upward distortions. Okay. Okay, now, but what is maybe even more interesting to us is not just that you have downward distortions when you have first-order stochastic dominance conditions, but also, by the way, this result is very general, can be generalized, which we do in the paper. But what is more interesting is how the distortions depend on the properties of the impulse responses. In particular, how, for example, whether it's true that higher types have lower distortions. So how distortions depend on the types. And here, as you can see, you can get all kinds of strange situations. So the distortions don't have to be monotonic in the types. So it's not true, for example, in the static setting, usually the lowest type is the most distorted. The highest type is not distorted at all. And also, it's easy to make assumptions. Actually, Eric has a nice paper which shows that under some assumptions, the distortion is monotone in types, which gives rise to quantity discounts. Right? So higher types have lower distortions. And the way it can be implemented is by giving kind of discounts for by larger quantities so that the marginal price goes down for higher types. Okay, so that's true usually in the dynamic model, but in the static model. In the dynamic model, it's a lot more subtle. Okay, so here's a simple example. So let's suppose you have a finite type interval in period t, and suppose that look at the types that are the endpoints of the interval, the highest and the lowest types. Okay. Suppose that you have positive densities at the endpoints. Of course, you don't need to have positive densities, but imagine that you do. So if you have positive densities at the endpoints, look at the impulse response and see that, okay, the denominator is going to be positive, but the numerator will actually be 0. Because when you are at the corner, okay, the CDF is 1 and is not going to be responsive to the previous type. So intuitively, if you're kind of stuck at the corner, and if your previous type were a bit lower or a bit higher, you would be at the same corner. So your type here is not responsive to the previous type. Well, in that case, the impulse response is 0. Okay, so you don't distort anymore. And furthermore, when you have a Markov process, it means you just stop distorting forever because you sever this chain of causation. Okay, and so the impulse responses in the future, they all turn to 0. Okay, because it's a product. One of them is 0, so it all turns to 0. So you stop distorting as soon as you hit one of the corners. Okay, in these settings. So what this means, obviously, is that you have non-monotonicity. At the lowest end, you don't distort. At the highest end, you don't distort, but in the middle, you distort. So you have a non-monotonic distortions in the types. Okay, now, of course, it's just a special case, but here's another way to sort of
If I remember correctly, there in the optimal tax literature,
yeah.
there are some
It's about continuous types more than a non-dynamic.
Hmm?
It's about continuous types more than a non-dynamic.
Yes, it's continuous types.
Then you
and
get
you
zero
have no
distortion
distortion
at the
at the top and no distortion at the bottom under certain. The top is you always get, but the bottom under some conditions.
So there are situations where I have no distortions at the ends and distortions in the middle.
That's right.
Okay, so I'll have to look at that. But
It's just an optimal control problem.
okay, yeah.
Because it has to be 0 at both extremes.
All right, but obviously here the driver of this is different. But yeah, okay. So another way to another interesting example is to look at nonlinear autoregressive process where the type in period t is some function of the previous type plus epsilon. Okay, and the epsilons are serially independent. The impulse response is the product of the derivatives. So here the derivatives are just the phi primes. Okay, so if you increase the type in period t, how does this affect future distortions? Well, that depends on the concavity of function phi. Okay, so if the function phi is concave, then increasing type in period t will reduce future distortions. But if it's convex, it will increase future distortion. If the function is linear, you have linear AR, then it doesn't really affect future distortions. Okay. Also, it's not necessarily true that distortions are decreasing over time. It's sort of a natural tendency, just because usually kind of the more longer you wait, the smaller is the link between this information and the initial information. But sometimes if phi prime is 1, sometimes it might be 1, and then in those cases distortion could increase over time. Okay, so this is just solutions of the relaxed program, but well, later on just to make sure that these solutions can actually be implementable, so we'll offer sufficient conditions and some examples where you can actually maintain solutions with these properties, make sure that they're actually incentive compatible. Okay, so you can also, if you interested in the case of discrete types, you can also apply kind of a similar discrete technique to discrete types. And I don't know if you're interested, but there is a paper by Battaglini that looks at the two-type case, and we are just interested. We wanted to compare our results to his results and see which of his results are general and which depend on the two-type assumption. But with discrete types, the way you should think about it is that kind of you replace the first-order conditions with the downward adjacent incentive constraints, and you can use sort of discrete impulse responses instead of continuous. I'm not going to write out the whole machinery you can imagine can be used. But for example, let's say you have two types, a low type and a high type. Okay, and then you have the Markov process on these types, where so the high type with probability QH remains high, and with probability 1 minus QH becomes low. And the low type with probability QL becomes high, and with probability 1 minus QL remains low. Okay.
This is still for profit maximization?
Yes, there's still profit maximization. It's basically the same, except you have two types. Okay. So, and first order stochastic dominance, which assumes that the QH is greater than QL. So if you have high type today, you're more likely to have high type tomorrow. Okay, well, so it turns out it's convenient to think about it again using a independent shock representation. Okay, so think about a state representation. So each period you draw epsilon independently from a uniform distribution, and this epsilon determines whether your type changes or remains the same. Okay, and the way you can think about this, so this epsilon can be between 0 and 1. Okay, so if epsilon is high enough, then your type will be high no matter, your type will become high no matter what. If epsilon is low enough, your type will become low no matter what. But if epsilon is in the middle interval, then your type will be preserved. Okay. So that will implement these transition probabilities using independent shocks. Okay. Now, why is this a useful way to think about it? Well, then you can sort of understand immediately what the impulse responses are. And the point we want to make is that if your type switches from L to H, okay, if your type switches from L to H, that means that epsilon was in this middle interval. But that means that if your previous type were H, your new type would be also H. Okay? So if epsilon was high enough to switch you from L to H, then it's definitely high enough just to keep your H that it was. So that means that as soon as your type switched from L to H, the impulse response is 0. Okay, that means that if the type is H and yesterday it was L, that means that your type would be H no matter what you had yesterday. Even if it were H, you would still have H today. Okay, so that means that once your type switches from L to H, there is no distortion. Okay, and of course the distortion, because it's a Markov process, it disappears forever. Okay, so this is Battaglini's what calls generalized no distortion at the top principle. Okay, so basically it's the same situation as what we had with the continuous model when you have a positive density at the top, because you kind of get stuck at the corner. And once you get stuck at the corner, you get 0 impulse response. And this will be true even if instead of 2 types, you had any number of types. When you get the highest type, you stop being distorted. But of course, it's not true if you have a type that's not the highest type. It's only true with the highest type. Okay, and so the point is, if you have more than two types, you only have this result applying to the highest type, and so. But what happens when you have many types? It becomes complicated, and we would argue that actually, when you have a large number of types, then the continuous model is better suited to study this. You'll get similar dynamics to the continuous model. Okay, so now I turn to the sufficient conditions. So I was just describing the relaxed program, and now the question is, well, what did I just waste my time describing something that's not incentive compatible? So we need to make sure that the solution to the relaxed program can be implemented. So when is it true? How can we check that? Okay, so what do we mean by being implemented? We want to implement it in the strong way, in the sense that when we talked about necessary conditions for incentive compatibility, then we could use a weak version, which is just Bayesian Nash equilibrium, because necessary conditions are even better if they apply even to weaker notions of incentive compatibility. Now, for sufficient conditions, we'd like to have conditions that give you stronger versions of incentive compatibility. So instead of just Bayesian Nash equilibrium, we actually will want to build a perfect Bayesian equilibrium so that you don't just have optimality at the beginning, but also optimality at all information sets. So now, what kind of strategies do we want to describe? There's this Meyerson relation principle will tell us, well, we can just focus on strategies that are truthful on pass, meaning that if you have been truthful so far, you will be truthful. But what will you do off pass? Well, that's sort of a bit of a problem. What will you do after you lied? Maybe you will want to lie again. So what we will do is, in the cases where we can do it, we'll actually be able to sustain strategies that are strongly truthful, meaning that they're truthful even after you lied. You will revert to being truthful. So this, we'll call them strongly truthful strategies. Okay, so, and to be sure, it's not always true that we can sustain strongly truthful strategies, but so far the sufficient conditions that we have are only, we have been able to apply them mostly in those situations. Okay, now for perfect,
so
yeah?
You're saying whenever you have conditions so that your first order conditions are sufficient to satisfy all the IC constraints, you also get strong truthfulness for free?
Well, it's not for free also. It's at the cost of some assumptions. But
you have to make additional assumptions for strong truthfulness.
Yes. But the question is, can we do it without strong truthfulness? And we had maybe a couple of examples where we could do it, but we don't have anything general so far, which is, I think, is the main weakness. Okay. It will have to do with Markovness, as you would probably expect. So, also, okay.
But this is assuming that others reported truthfully.
Yes. Okay. Well, we have to define beliefs. Okay, and so they will just define beliefs this way. We are free in perfect Bayesian equilibrium. We have substantial freedom about defining beliefs. They have to satisfy Bayes rule, but otherwise, there's a lot of generality. So by beliefs, I mean that each agent, given his reports and his true types, has. So this is his. This is his information set: his reports, his true types, and his consumptions. And he has to form beliefs about what other types were and what they have reported, which in principle could be two different things. Okay, and so beliefs have to be consistent with Bayes rule, but here actually it's a mild requirement. Of course, because we have continuous types, then that means you can change beliefs at any zero probability point and still be consistent with Bayes rule. Bayes rule is just defined on positive measure events. Okay, and so we construct beliefs where the agent believes that everybody else has been truthful. And also, it seems natural to construct beliefs so that beliefs about the others do not depend on your types. It's in the spirit of not signaling what you don't know, because your type is not correlated with the other types, with the other agents, so you shouldn't make any inferences from your type. But your beliefs will be functions of your reports, because your reports could affect the other types through decisions in some way. But your true types have no way of affecting other agents' types. Okay, and so with these beliefs and with the allocation rule, that defines the stochastic process from the viewpoint of the agent. So this is the stochastic process that the agent forms over the future. Okay, and this stochastic process, yeah?
I'm sorry, on the previous
All right, yes.
You're already assuming that types are independently distributed.
Yes.
So that knowing my type
Yes.
tells me nothing
Yes.
about what you're doing. So how does this if you believe other agents are being truthful, how does this differ from
Yeah.
independence?
Well, so this is, of course, on zero probability events is where it matters. So off equilibrium.
I see.
So,
Okay,
right, in equilibrium, you're reporting truthfully, so it doesn't matter. But when you lied, the question is when you lied, do you make an inference about others from the fact that you lied? Okay, so that, yeah. So basically, when you lie, you don't make, you think about the others. They might depend on your reports because your reports affected the distributions, but your true types didn't affect distributions, so you don't, okay. All right, so then anyway, so the notation is a lambda. Given these beliefs, you have this probability measure over types, and that when you look forward using the kernels, the allocation rule, and using the beliefs. Okay, and we just define this as conditional. This would be conditional on the whole state that has been realized and kind of up to yesterday and the agent's types. Of course, it will only depend on what the agent observes, but it's just notationally convenient to write it as a function of everything. Okay. Anyway, so once you have this, you could say, well, now this will be a necessary condition for perfect Bayesian equilibrium. Of course, ICFOC will be a necessary condition for it, but why just limit yourself to period 0? In every period, you will have to have this a version of ICFOC in every period, okay? Because it means that the agent is optimizing. So this is on path. So if you have been truthful, but you know it has to be optimal for you to continue being truthful given your beliefs, so that ICFOC has to hold. So this is your expected utility from continuing to be truthful on path in period t given what happened. And so by analogy to what we did before, this will be another necessary condition, ICFOC. So it's the same formula, essentially, but written starting in period s. S is the starting period, instead of starting in period 0. And the impulse responses here will have to have another index, which is s. So this will be the impulse response from period t to period s. Okay, but otherwise, it's basically the same. It's just like a shift in time. And we have to strengthen our assumptions a bit so that they apply not just in period 0, but in all periods. Okay, so this is now we have this whole set of ICFOCs that in all periods and for all kind of possible histories. And we want to, and the question is, when you want to sufficiency, so when you want actually to have a mechanism that implements this allocation rule, this mechanism, so the payments in the mechanism have to satisfy all these ICFOCs. So it's still just a necessary condition, but it's a much kind of richer necessary condition. And the question is, can we do it? And so the first thing we'll show is that, yes, we can construct payments to satisfy all of these conditions. Okay. And there's also one technical issue about the payments, is that because we have this infinite horizon, there's an issue about how do you spread those payments over time. You cannot just wait until the end to make payments, so you have to spread them over time. There's no end, in principle. And then when you spread the payments, the payments have to be spreadable. So what does it mean? So the definition of spreadable is that you have to represent the payments as the net present value of some payments per period. And the restriction is that these payments per period have to be, there's some index t here, it's missing. Okay, so the payments per period have to be absolutely integrable. So that basically, so condition 2 means that they have an expected present value in the sense of double or Begg-Stiglitz integration. And the reason that this is important is that you should want to be able to interchange summation and expectation. It's like Fubini's theorem, right? So that otherwise you get all kinds of paradoxes. So that's, if your payments don't satisfy this condition, that's not acceptable to us. Okay, so we want to construct payments that satisfy these conditions. Of course, with finite horizon, it's all trivial because you can just pay at the end, it doesn't matter. So, but it's kind of, but so to make sure it's true, we impose a certain condition on utility, an extra condition which we call continuity at infinity. Questions? Okay, so you don't have to actually read this condition. It's not very restrictive, but it's some kind of bounds that utilities cannot, in the future, cannot be very huge. I mean, they could still be large, so they're not really bounded, but they're bounded relative to the types. We don't necessarily have them. No. We don't want them to be actually bounded. But so this idea that utility can be spreaded over time as well in some way, so that the utilities in the future are somewhat bounded, not bounded by some fixed number, but bounded relative to the types. Okay. So anyway, so under this assumption, so we have this theorem that says that for any allocation rule, you can construct transfers that are spreadable and that satisfy this ICFOC in all periods. Okay, so that's how do we prove it? Okay, that's a bit of yeah.
Come back to
Yes.
something you said.
Yeah.
You said that one justification for looking only at the initial IR constraints
Right.
is that you can imagine the agent posting a bond,
Yes.
which he will get back, which he will forfeit if he leaves.
Oh, yeah. Of course, it has the same issue. It has the same issue of when do you pay it back.
Yeah, exactly.
Yeah. Well, we didn't. Okay, so we didn't formally deal with this issue, so we sort of swept it under the rug. But my impression is that we would be able to pay it back as long as you pay it back sufficiently slowly. I mean, there has to be a similar technical condition. I think to deal with it formally, you'd have to make some assumptions about the IR constraints, how they change with time, as long as they change with time in some kind of well-behaved way. I'm not sure what it should be. Then you should be able to do it by postponing the repayment enough, but still not too much, so that you still satisfy the spreadability condition. Otherwise, if you have to pay too much at the end, then that will fail to satisfy this condition. Yes. Yes. So we didn't do it formally, but I think it could be done, but
It might be. Since you've
Right.
taken care of this,
Yes.
it's a natural thing to take care of that.
yeah, we could. Although I guess in some sense, in a model where there's no participation constraints in the future, then we don't have to do it. But the question is about which assumption is more realistic. And, yes. So there is a set of assumptions under which we don't have to take care of it. So, and then there's some hand waving that says that maybe it will still work. And obviously with finite horizon, that's not an issue. So. Okay, so then how do we construct the payments? Okay, it's a bunch of formulas. I'll see. But I mean, the idea is really very simple. So I'll try to walk you through these formulas just in terms of the ideas. So first of all, we define this DIS. So what is DIS? Well, DIS is exactly this right-hand side in ICFOC. So just exactly this, but in period S. So it has to be done in every period. So this is basically how much the agent's, this should be the derivative of the agent's utility in period S with respect to his current type. And it has to satisfy, it has to be exactly this. So that's our goal. Okay, now how do we go? Well, of course, we want to integrate this with respect to the type in period S, because that should be sort of the agent's total utility up to a constant in period S. So this will be our QIS. So basically, we want to make a payment to the agent so that, in period S, this payment is, up to a constant. This payment plus utility in period S has to be equal to this up to a constant. QIS is sort of the goal for the agent's total utility in period S. And this is sort of what we do. So we construct this payment, well, now in period T. We give this agent QI. But of course, the problem is that there's also the future. This is not the last payment the agent gets. There's also the future in which he will get more payments. And that will, anticipating the future, will change his incentives. So you have to offset it somehow. And that's why we give this other term. So this next term will offset the agent's incentives in the next period. Okay, the first term is just, if this was the last period, we'll just give this term. Okay, and what is the third term? The third term is just basically his utility function, because the payment plus utility function has to equal to Q. So the point is the agent's payment plus utility function has to equal to Q. And there's only the thing is that there's this extra term here which will offset his future incentives. So that in the end, in period S, in period T, he will just worry about Q. All right, and so once we did this, then this is a proof that it will work. So we calculate the agent's expected utility in period S. So conditional on what he learned in period S, he takes his expectation. And then, but when you look, the expectations, he takes the sum of his utilities and the payments in all periods. But of course, the history is already fixed. So the fixed history does not affect his incentive. So there's just some function of theta a minus 1, and some function of theta s minus 1 does not affect his incentives. So that's fine. Then the current term will be QIS, and then there will be also a bunch of future terms. But the way we constructed these future terms is that they will all be canceling each other, except for the last term. Of course, what's the last term? There's no last term. But you take the limit of cap t that goes to infinity. So if you took a partial sum up to cap t, there would be a last term. But then when you have to sum to infinity, that means you take the limit of the last term, and the limit of the last term will go to 0, so it will disappear. And the only thing that will be left is just this term, which is exactly what really we want, because it ensures that this ICFOC is satisfied. Okay, so QIS is exactly what the utility we need to give to the agent to satisfy ICFOC. Okay, so I hope at least intuitively that's clear. Okay. Okay, so what is also kind of interesting, and this is something that Emmanuel talked about, is not only that it's possible to satisfy ICFOC, but essentially there's only one way of doing it. Okay, so this is what we call payment equivalence. So this is like revenue equivalence in static setting, but it's just a little bit stronger because it's just not just an expectation over the future, but also for every realized sequence. So it has to be, as a function of the realized sequence, it has to be nailed down up to a constant. So this is true with one agent. Of course, with many agents, you still can take expectations over the other agents' types. All right. So here I actually tried. I don't know if that's feasible. Okay, I'll try to kind of walk you through why it's true. Okay, so Emmanuel said it's true. I'll try to walk you through and so why it's true. And the idea is that you have to do it sort of. So what you know so far, what ICFIC tells you, let's say, if you look at this one, it just tells you that if you take expectation period 0, the derivative of the expected utility will be nailed down. But this has an expectation. But you have to get rid of the expectation, unravel it. Not just the expectation, but the realized utility has to be the same. And the way you do it is by looking at the changes in this as you go over time. So this is the change if you look in period S, minus, so expected utility in period S minus expected utility in period S minus 1. And use the iterated expectations because you can write the expected utility in period S minus 1 as the expectation of the expected utility in period S. Okay? So now what you have is a change in VS, kind of the change between your prior expectation and the realization of VS. But this one will actually be nailed down because VS satisfies ICFOC, so this change will be nailed down. Okay, so in other words, as the agent gets more information, each time he gets more information, you know exactly, the ICFOC tells you how much his expected utility will change. And then, of course, the same will be true for payments, okay, because the other part is just utility, it's also fixed. So, so if you look at the expected utility of total payments, as the agents get more information, we know exactly each time how much his expectation of the payments will change. Okay. And then, when you take S equal to infinity, what happens? Well, you can show that basically you will get the realization of the payments under some, basically if psi is spreadable. If psi is not spreadable, that anything crazy can happen. But the spreadability assumption will ensure that when you take, so ask what is your expected total payment in period S? Of course, if S is large, then you already found out a lot. And as S goes to infinity, you will actually, in the limit, find out exactly what you're getting. Okay, and so it converges to what you're getting, while what you get on the right-hand side, this is a prior. And the prior, so basically when you add these things up, on the right-hand side, this is take the expectation period 0, which is just a constant. Okay, so the result is that the total payments will be nailed down up to a constant, it's probability 1. So this is with one agent. Now, of course, with many agents, suppose you have autonomous kernels, which means that they have completely independent stochastic processes. And the same is true when you take expectations of agent i's payment, this is psi I, over expectation over the other agent's types. So this is just standard. And they can be generalized to more general processes, but need some assumption there, which I'm not going to mention. Okay, so it extends to all even though I used perfect Bayesian equilibrium for this, but actually it also holds for Bayesian Nash equilibrium choice rules. You don't need the stronger incentive compatibility. Now, so is this important or not important? We sort of had some debates with authors about whether this is important or not. And in some sense, in the case of quasi-linear utilities, and the only thing that matters is expected payment. So why do you care exactly how they should be spread over time? It doesn't matter. But on the other hand, in the kind of model that Manuel talked about this morning, when you care about consumption smoothing, so instead of payments, replace payments with some function of consumption. So there, it does matter a lot how consumption is spread over time, because some spreads will be cheaper than others. You maintain the same total psi to give the agent incentives, but the cost of this to the planner will be very different. And so you can optimize the spread, but you know that basically the spread is uniquely given to you from the incentives. Okay. Okay, now sufficient conditions. So so we don't have, so far I haven't given you sufficient conditions, so I'm getting there. It's a bit of a kind of slow process. Okay, now how do we ensure that we can sustain strong truth-telling strategies? Well, of course, the easy way of doing it is to assume that we have a Markov setting. So what is a Markov setting? This is a setting where, first of all, the history of your types doesn't matter. Only the latest type matters. Okay, so in other words, the distribution of your type today depends only on your type yesterday. It does not depend on any previous types. And also the utility function, when it's written as a sum, you spread it over time, then you say in every period it's a function only of your current type. So similarly, when you look into the future, the only thing that matters to you is your current type. Your previous types don't matter. So this is a Markov setting, of course. Of course, it's in terms of your reports, it will not be generally true, because the allocation rule can condition on your report. So your previous reports will matter, but your previous true types will not matter. So why is this useful? Well, that means that if you are truthful on path, you will also be truthful off path. So does it matter to you that you lied? Well, the only thing that matters is what you reported in the past. But what your true types were in the past doesn't matter anymore. Okay, so if you were truthful, if it's optimal for you to be truthful on path when you were truthful, then it should also be optimal for you to be truthful off path. Your incentives are exactly the same. Okay, your past reports matter, but your past true types don't matter. Okay, so of course Markov is a strong assumption, and we'll try to generalize it a little bit, but it's hard. So you're welcome to. I'll talk a bit later about this. So let's focus on Markov first. Okay, so and then so we focus on strong truth telling, so which are always truthful even off path. And here's our kind of theorem for the Markov settings. So if you have a Markov environment satisfying all kind of our previous assumptions, and if the allocation rule satisfies this condition, which we call weak monotonicity, then it can be implemented in a strong truth-telling perfect Bayesian equilibrium. Okay, and so what I'm going to do now is trying to sort of interpret this condition, what that means, okay, and how we can ensure it. So what is this weak monotonicity? So obviously it's somehow related to this static setting that we described yesterday, where it was the monotonicity of the allocation rule. But of course, the allocation rule now is a kind of, it's a dynamic setting, so it's a more complicated thing. So in some sense, some kind of monotonicity in aggregate or on average. Okay, so what is this average? Well, this expression is actually, you can interpret it, it's very similar to ICFOC. So it's very similar to the derivative that you had on the left. But the difference is it's taken after the agent has misreported his type in period t theta I hat t. Okay. So in a sense, this thing will be the derivative of the agent's expected utility with respect to the true type following a misreport of the type. And the assumption is it has to be non-decreasing in the misreport. So the higher type he reported, the higher should be this expression. Okay. So what are the steps? So I'm going to interpret this a bit more later. Okay, so for now, just outline. So what are the steps in the proof? So the first step I already explained. So first we have to satisfy the IC, FOCs, and all the periods by constructing payments. I already described that this can be done. Okay, the second step is this step about ruling out, using this condition to rule out one-stage deviations from truth telling. Okay. So this condition will ensure that the agent will not want to have one-stage deviations from truth-telling. Now, with infinite horizon, that's not quite enough. So you have to worry about infinitely lasting deviations. And so you have to derive some version of one-stage deviation principle. Unfortunately, the standard version doesn't quite true if utilities are unbounded. But basically, we can, under the assumption that we made, we can ensure that even though they're unbounded, but in such a specific way that you can still basically make sure that the tails are small enough, so that the tails will never tempt the agent to deviate.
So at this case, you can't deal with the case where if I lie, I'm not able to tell the truth tomorrow. So you have a moving support, for example.
We allow the agent to report anything. So even if you have moving support, he can report outside of the support. Even then, we have sufficiency. Yes. So we don't force the agent to report something in the support. He is allowed to report outside of the support. I mean,
you even define the allocation.
well, as long as it satisfies this, you can define it.
So you extend it there.
Yeah, you can extend it. Yeah. Yeah.
So in the standard setting, you need both the monotonicity of the allocation, but also some condition on the utility function.
Well, so this in a okay. Well, in a sense, it merges everything because here's this. This is utility function is also here. Okay. Okay. Good. So later on, I'll break it up. I'll say that here are sufficient conditions on the allocation and the utility function that ensure that this whole condition is satisfied. Now, also in the static setting, you can also have stipulate an aggregate. Then you don't need separate conditions as long as the aggregate condition is satisfied.
This is like going through the sufficiency proof with the gains for misreporting.
Oh yeah, okay, hold on, I'll do that. I'll go through the proof. That's exactly it. So how do you prove that one-stage deviations are unprofitable? Yeah, it's very similar, okay. So let's define WT to be the agent's expected utility from reporting data I hat T at some history, and then followed by truth-telling. And so the way you can think about it is that data I hat T, think of it as an allocation. It's a one-dimensional thing. So think of it as an allocation chosen by the agent. And the agent has this kind of utility function for this allocation. Then weak monotonicity is basically the single crossing property between this allocation theta I hat T and the agent's type theta IT. Okay, now what do you want to implement? You want to implement truth-telling, which is a monotonic allocation rule. It says that your report should be exactly equal to your true type. It's a monotone function. Okay, so then we can apply that result and say that if the single crossing property holds, then you can implement this monotone function. Okay. As long as you also satisfy the first order conditions, which we know that we can do satisfy. Okay. Okay, now if you put that all together, this is kind of a long corollary, but basically it says that under some assumptions, the relaxed program is fine. You can just, okay, so basically under all the assumptions we have made, in addition, okay, to make sure that we satisfy all the participation constraints, we assume that the utility is non-decreasing in type. Okay, so in that case, and we also assume first order stochastic dominance. In that case, suppose you have an allocation rule that solves the relaxed program, meaning maximize expected dynamic virtual surplus. Okay, and suppose that this allocation rule satisfies weak monotonicity. In this case, okay, first of all, we can construct a payment rule that's spreadable over time that sustains strong truth-telling in the perfect Bayesian equilibrium. The lowest types participation constraints bind. All types participation constraints are satisfied. This maximizes the principal's expected payoff among everything. Furthermore, if this is true, then any optimal allocation rule must maximize expected virtual surplus. So you're not missing any allocation rules by maximizing expected dynamic virtual surplus. And furthermore, using randomized mechanisms will not increase expected payoffs for the principal. Although so far we didn't look at randomization, you can think of randomization as conditioning on the types of some fictitious agent for some random type. But of course, if you're maximizing expected dynamic virtual surplus, there is a reason to condition that doesn't affect your objective function. And so that so the last part basically implies that you don't need to use randomizations.
And do you have any condition that guarantees that it would satisfy the allocation rule would satisfy?
Yeah, it's coming. It's coming. Okay. So now, okay. So these are stronger conditions. Okay. So now I'm going to make conditions that are stronger but easier to check. Okay. So that condition is kind of not very strong but hard to check. Okay. So first of all, if you have an autonomous process and we look at the expectation, it doesn't depend on the allocation rule. So you can ensure that the expectation is monotone by making sure that every term is monotone. So we call it ex post monotonicity. So instead of taking expectation, you look at just every realization and say that every realization of this is monotone and call it ex post monotonicity. Okay, now let's make it even stronger. How do you ensure that this is monotone? Okay, let's assume first order stochastic dominance. That ensures that all the impulse responses are positive. Positive. Okay, also single crossing property, which ensures that all these derivatives are increasing in the consumptions. And let's assume that the consumption of agent I is non-decreasing in the type of agent I. Not just in the current type, but actually in all the history. So let's call it strong monotonicity. So every component of the consumption is non-decreasing in every component. So if this holds, then you can check that the ex post monotonicity will hold. If ex post monotonicity holds, then weak monotonicity will hold. And then you can implement it. So this is obviously strong property, but it's very easy to check when it's true. And furthermore, we'll make assumptions on the primitives that will ensure that it holds. Okay, so by the way, it's just a kind of footnote that when you have strong monotonicity, then you can ensure some sort of robustness of the mechanism. So not only implement in perfect Bayesian equilibrium, but even if agent I can sort of spy on the other agents and find out the other agents' types, and even find out their future types, it's still not going to give the agent any incentives to deviate. So some robustness. You cannot ensure full robustness because if agent I can spy on his own future types, that will give him incentives to deviate. He has to be Bayesian with respect to his types, but he doesn't have to be Bayesian with respect to other types. Okay, anyway.
So it means it doesn't matter what his probability distribution over the other types is as long as he expects them to tell the truth.
Yes, if these conditions are satisfied. Yeah, have strong monotonicity in these conditions. Yeah. Okay, so questions? Yeah. Well, first order stochastic dominance is basically saying that the CDF is decreasing in the past types. So the derivative is negative of CDF with respect to past types is negative. Because that's what gives us the impulse responses being positive. Okay, but for example, in the Corti and Lee in the second, in the example where they don't have first order stochastic dominance, in the example weak monotonicity still holds, but this of course doesn't hold. So it's by no means a necessary condition. It's just one that's sufficient and easy to check. Okay. Here's another example. So when we go back to the previous example with a time separable utility, ex post monotonicity means that some weighted sum of consumptions, some discounted weighted sum of consumptions is increasing in your report. This is ex post monotonicity. But it's weighted by what? By the discounting and by impulse responses. Okay? So let's just specialize it again to nonlinear autoregressive process where you calculate the impulse responses by using the phi primes, the derivatives of phi. So the question is, how do you ensure ex post monotonicity? Well, it can be ensured by assuming some bounds on the phi prime, that they're kind of small enough, together with discounting, ensuring that this is non-decreasing in the report. And then, okay, so doesn't matter what the numbers are, but here's the intuition. Okay, so here you can violate strong monotonicity if your current type reduces future consumption. But maybe this effect is not so big because your current type, because just of the efficiency effect, it will increase your current consumption. So as long as you're not very patient, it will be okay because you have to just take in some sense, the net present value of consumption weighted, of course, by impulse responses. If the impulse responses are not very large and the discount factor is not very large, then the future will be overwhelmed by the present, and so you'll have enough efficiency effect will be strong enough to ensure weak monotonicity even when you don't have strong monotonicity. Okay, so you don't. So that means that, of course, strong monotonicity is not, crucial for sufficiency. Okay, now as I promised, sufficient conditions on the primitives. Okay, so what if you don't know what the allocation rule is, but can give sufficient conditions on the primitives that ensure that the solution to the relaxed program is strongly monotonic? Yes, so you can do it. It's kind of similar to the static setting. You have a similar condition for the static setting with one difference, which I'll point out. So the conditions are, okay, the process is autonomous, so it's not controlled by decisions. First order stochastic dominance. Okay, xit, it's Euclidean. So allocation rule, there exists some allocation rule to maximize expected work surplus that x is a lattice. So basically, if you have a kind of a multi-dimensional problem, then all the dimensions have to go in the same direction. Otherwise, you might have various kind of countervailing effects. And the virtual utilities of all agents have to basically, they have to be supramodular in the allocations and have this increasing differences, meaning the single crossing property between types and x. So in this case, the relaxed program has a solution that is strongly monotone. Okay, now of course the supramodularity assumption here is somewhat strong. It holds for public good settings, but in auctions actually you have substitutability among agents, because if I get the good, so then x is not a lattice, because if I get the good, that means somebody else doesn't get the good. But it's okay, it can be applied to auctions, because it's enough you can just show that my allocation is increasing in my own type. You don't have, my allocation can be decreasing in the other types. That's okay. You can just show my allocation is increasing in my own types, and you still get strong monotonicity. That's enough. Okay. Now, of course, the key trick here is how to ensure that the virtual utilities have increasing differences, or the single crossing property. So remember, these are our virtual utilities, our utilities minus this information rent term. And basically, the difference from the static is these impulse responses that are now here and were not here in the static setting. So the assumptions in the static setting are, of course, you assume that the utility has the single crossing property or increasing difference. Okay, but you also need to make a third derivative assumption. You need to make sure that this minus d2 respect to theta has a single crossing property, which is a third derivative assumption. And these are sufficient conditions that ensure, also, of course, that hazard rate is non-decreasing. So together with this, it ensures that the whole thing has the single crossing property, which ensures that the solution is monotone. Okay, but here you also have these impulse responses. So what you need to do, you need to assume that impulse responses are non-increasing, so that the higher have lower impulse responses. So this is the extra thing you have to do in the dynamic setting relative to the static setting. Okay, so intuitively what it does, it ensures that higher types, they have lower impulse responses, so there is less of a reason to distort them. They receive lower distortions, which contributes towards the monotonicity. Okay, so that the consumption will be higher. But of course, it's not an innocuous assumption. It's a pretty strong assumption on the stochastic process. Okay, and as we actually went through examples where sometimes it's satisfied, sometimes it's not satisfied. So then you do get sometimes non-monotonicity, so that higher types can receive, they can have higher impulse responses, and they can receive higher distortions sometimes. So, okay. Questions? Of course, these are strong assumptions, and they give you strong monotonicity. And as I said, in some other case, you don't make these assumptions, you could get still weak monotonicity, but that's something you'd have to check on a case-by-case basis. Have a general theorem that will guarantee that the solution satisfies weak monotonicity if it doesn't satisfy strong monotonicity.
If you were to go away from the quasi-linear case, do you think you could get a condition like this, or is it much harder?
Well, I think of your case as quasi-linear because, you just call the payments, call the function of consumption, call them payments, and so your case is covered. Except, wait, sorry. Okay. Your case is covered, except for, of course, your maximization problem is a different problem from mine. Yes. So then the answer is no. But what your case is covered, this theorem, the previous theorem, this theorem covers your case. Okay. Okay. The next theorem doesn't cover your case. Yes. Okay. Fine. All right. Sorry. All right. So okay, I'll just give you an application. Let's see how much time maybe I'll skip this application. No, I have time. Okay. So an application to bandit mechanism. What's a bandit mechanism? Okay. So the two-armed bandit problem. So you have different arms, and you don't know the probability of winning on each arm, and you can sort of experiment until you find enough information where you can settle on one of the arms. This is, of course, a problem that's not just for gambling, but there are many applications. Online auctions, when a search engine puts some advertising, but it doesn't know how successful the advertising will be. It experiments. It puts an advertising, see whether people click on it or not. If people don't click, it will replace it with some other advertising. Okay, but of course the people, advertising is supplied by some other people. So there's an auction. So you set up an auction or a series of auctions where these other people are bidding on the advertising, and they have some values that are evolving, and they're learning. Okay, so this is sort of loosely motivated by these kinds of problems. So here you have several buyers who are bidding in an auction for some good. Okay, sorry, that should be the slide. Okay, so you have one object and a number of buyers. The principal is a seller, and the seller can give the object to different buyers to sort of try it out. And the values of buyers evolve. And actually, if you get the object, then your value gets a shock. And the idea is that you sort of learn something about your value. If you don't get the object, that your value doesn't get a shock. Okay, and actually, you can say that you could make sure that the variance of the shock can depend on how much you have had it before. Of course, if that's the first time you get it, you get a high variance because you're learning a lot. So this will come out of Bayesian updating with some joint normal distributions, for example, right? So in this case, your sufficient statistic is just your mean, and your mean is updated as you get more information. Of course, eventually, when you get more and more information, the updating becomes weaker. So you can sell the object, give it to different buyers to try it out. Okay, and then the nice thing about it, this is just makes it really, really simple. Is the values are basically follow kind of like a random walk. So the shocks is always additive, and that means that the impulse response are always 1. That makes it really simple. Okay, so this is your the dynamic virtual surplus. This is your relaxed objective of the relaxed program, where you're maximizing the total expected virtual value instead of the true value. Because the impulse response are always 1, here you're just subtracting the inverse hazard rate. So there's nothing to put here. Okay. Yeah? Yes, they could. Impulse response are still 1. It's not autonomous. Yeah, so we have to check weak monotonicity directly. Right, so the thing about this application, so here you cannot use this other conditions. You have to go, the weak monotonicity condition applies to general processes. That's a complication that you have to deal with. But we do it, so we check it, okay? Or Ilya checked it, okay? I believe him, so. Okay, so now, but the optimal mechanism is, in this case, any time you have this kind of linear autoregressive process, the optimal mechanism looks like a handicapped mechanism, in the sense that in the beginning, when you report first, your report determines your handicap, how much you are disadvantaged in the future. And then from that point onward, you basically implement efficiency with the handicap. So the handicap is sort of, so the seller sort of imagines that his cost of serving you is, actually it should be a plus, I think, instead of minus. So that your cost is increased by your handicap. Okay? So the high, but of course the higher report you make, the lower will be your handicap. So if you report the highest possible type, then you will be treated efficiently. Okay, but if you report a low type, then there will be distortions. Okay. But then what do we know about efficiency? So in this case, fortunately, of course, it's not a very simple dynamic programming problem, but there is an off-the-shelf solution to this dynamic programming problem, which is based on the Gittins index, which is something which, again, I'm not an expert on this, but my co-authors are. So that you just, the Gittins index intuitively calculate the expected kind of, you say, well, if you give the object to one agent, just to agent I for t periods, and calculate the expected per period value of doing that, and choose the optimal number t for this, and then this is the Gittins index for this agent, and then it turns out it's always optimal in every period to give the object to the agent with the highest Gittins index calculated based on the current information. And so we get exactly the same solution except with this handicap, okay, where you increase the cost of giving it to agent I based on his initial report. Okay, and the only thing is, how do you check that this solution actually satisfies all the incentive constraints? We check weak monotonicity directly, which is not so trivial, but there's no strong monotonicity here, by the way, because intuitively, so if I make a higher report today, that could give me the object tomorrow, but it could be that I get it tomorrow and find out actually my value is not so high, and that will reduce my consumption next period. So it's not true that my higher report always increase my consumption, but you can show that an expectation still does, so it's okay. Okay, now what about non-Markov settings? Okay, so with non-Markov settings, we are in a bit of a trouble, although, right, so the problem is that then agents will lie in different ways. So we have one example. It's a very simple example, admittedly, where we can actually sustain truth telling in a non-Markov setting. So this is an example where it's a sequence of auctions. So it's time separable, and the values of the buyers in the auctions follow an ARK process, autoregressive process. And of course, if k is greater than 1, it's not a Markov process. Okay, so this is the ARK process. So the epsilons are independent across everything. So here, the nice thing here is that you can just solve the relaxed program. It completely separates over time and over states. So in every situation, you give the object to the agent with the highest virtual value, where the virtual value is calculated by this. So of course, because of the linear ARK structure, the impulse responses here are constants. Okay, and so the only thing that matters really is your initial report. So again, your initial report determines your handicap, and then in each period you play a handicapped victory auction. Okay, so intuitively it's sort of like cost, you know, where you say I'll pay membership fee, and if I pay membership fee, I will get everything cheaper. Except that here you will have a menu of membership fees. It's a continuum. You can choose, you know, if I pay a higher membership fee, I will get, my price will be lower in all periods. So then it's obvious, it's very clear that strong truth telling is optimal starting from period 1. And the reason, basically, you're just playing a victory mechanism, like a victory auction in every period. It doesn't matter that you misreported. You know, your handicap doesn't, of course, your handicap will be determined by your report, but otherwise, history doesn't matter. Okay, and the only thing is that you need to check that in the first period you don't want to misreport, and that's also easy to do because basically our previous theorem about weak monotonicity and strong monotonicity and so on, it applies in period 0 no matter what, because in some sense period 0 you are Markov because there is no history there, so it still applies. So you can just check that you do get strong monotonicity, and that implies that in period 0 you don't want to lie either. So this is a non-Markov case where we sustain strong truth telling, but admittedly a very special case. And now let me talk about other non-Markov cases and what the problems are. Okay, so I'll just point out the problems, and maybe one of you will solve it. So the problem is, of course, finding the sequentially optimal strategy sigma I, which is how will you lie after you lied. Okay, there's one way to kind of Markovize the whole thing, which is Dobke and Townsend follow this approach. The idea is that you can always think of it as Markov as long as the state space is big enough. So if you allow the state space to include the whole history, then it's Markov. Yes. And what you need then to do is the agent has to re-report the whole history again and again. So in a sense, if you lied once, then in the next period, the agent can say, oops, okay, I lied in the past, but okay, now here's the truth. And fine. And then basically, it's sort of like the revelation principle without loss. It's a different version of the revelation principle, which without loss of generality, you can focus on situations, on mechanisms where the agent just always returns to being truthful and re-reports the whole history truthfully. Well, the question is, does it help us or not? And I'm not sure how much it will help us because, fine, you can look at truthfulness, but now you have multi-dimensional incentive constraints because it has to send a multi-dimensional report in different periods, and how do you then maximize subject of those constraints? So I don't really know how to operationalize this approach. Okay, so now there's some other special cases where we can establish sufficiency, which involves, so for example, there's a paper by some computer science guys, which actually sort of, it's a nice idea, but it also depends on some special nature of the process, where they use the re-reporting of the initial type, so that if you lied about the initial type, in the future, sort of a little bit in the direction of Dobke-Townsend, so, but they actually will give you like a chance to correct yourself and re-report the initial type, and they can check all the incentive constraints. And I also have worked with one student where we worked out the case of 2 periods. And the case of 2 periods actually is not so bad, but with more than 2 periods, it's still open. Okay, so I'll just summarize this. So we had the sufficient conditions for incentive compatibility, and trying to unify the literature and kind of understand the role of the stochastic processes, how the impulse responses determine the results and the nature of the distortions, and various new applications. Okay, I want to mention some extensions. So now just briefly kind of check off various things and possible extensions that people worked on, just to let you know what else is out there, and it will be a very limited list. So what if the agents, instead of just saying the agents like here from the beginning, what if the agents can arrive over time? Does it make any difference? Well, of course, as soon as the agent arrives, you want to sign him up for a contract because it minimizes information rents. So just sign him up based on the initial private information that he has. Well, of course, the problem is, what if the agent can arrive but doesn't have to come to you? He can just sit out there. You know, if arrival is private, you know, they actually may decide not to show themselves. Why? Because suppose an agent currently has a type close to the lowest type. Then he knows that he is not going to get information rents. But if he waits and his type will change, in the future he could get some information rents. So he might prefer to wait and come later. Okay. So then you have this also incentive constraints about how do you induce agents to show up earlier rather than later. So the Alessandro student Garrett had his job market paper on this, but he only worked out some special cases. It was a hard problem. Now, so that's one thing. Now, so consumption smoothing is something that you hear from the other speakers. Other situations, when I mentioned bonding, well, in a sense, bonding is costly because of consumption smoothing, right? So there's, and the dynamic taxation is one application of this. There are other applications, for example, you know, life insurance, and Handel and Lizeria has worked on this issue. So if you buy life insurance, also consumption smoothing comes in, so you don't just front load your premiums too much because people don't want to, you know, pay everything they have for premiums. And what this creates incentives for adverse selection, obviously, because in the future, if you find out that you're really very healthy, you can shop around and you know, there are participation constraints that will bind. So this is a situation, in other words, where participation constraints will be binding not just in the initial period, but all over the place, you know, all over time, and that will, of course, make for a harder problem to solve. Another paper with consumption smoothing is managerial compensation. Okay, dynamic taxation is some, okay. Another paper, so with Garrett and one talks about replacing the agent. And the idea is that, so suppose the agent is the manager, but of course, over time, what tends to happen is that because the impulse responses typically shrink over time, so the longer you keep the manager, the more efficient he works. And so that creates a bias towards not firing the manager, because if you have to hire a new manager, then you have to start out with this inefficiency again. So you want to keep the devil even though, of course, it's a stochastic process and the manager will become sometimes less productive, but you will still keep him inefficiently. Okay, so that, I guess, I'll conclude on these applications. And let me just say one more point, which is this everything assumes full commitment by the principal. And of course, you will notice that when you go in after the first period, this is not going to be efficient anymore because the agent has already revealed his type. So there is no reason to distort him anymore. There's a strong incentive to renegotiate towards efficiency and eliminate all these distortions. Okay, and this is something that we really don't look at. But of course, there is a big literature, and Eric was at the forefront of that literature on renegotiation. But it is still a very hard literature because it basically means that the principle doesn't hold. You don't want the agent to announce his type right away because that gives a very strong incentive to renegotiate. What you kind of instead do is you commit yourself against renegotiation by not finding out too much about the agent. So instead of revelation mechanisms, you look at some mechanisms. Typically, very often they involve randomization, where the agent, by randomizing, kind of has some partial separation, partial pooling, and that, of course, makes it a much harder problem. And so what seems to have happened is just because it's so hard, people put this issue aside and just solve the full commitment case. But I do think it's very important to go back and try to understand problems of commitment and solve the cases without commitment. Okay. Yeah.
So one reason why we like to use the first order approach in dynamic complexity problems is often that it gives rise to a very simple recursive representation of the optimal concept. Do your results have implication for that question too? Like the way we can maybe write down the whole problem in a simple recursive way?
Well, so far I didn't necessarily find that necessary, but I mean, in a sense, what the first order kind of, I have a somewhat different view, but maybe you could do it either way. So in my view, the way it works is that the first order representation basically tells you what the dynamic virtual surplus is. So instead of maximizing the true surplus, you maximize the virtual surplus. It is a dynamic programming problem, and so you might find it useful then to solve it using recursive methods. So I'm not saying that recursive methods are not used. So once you have a non-trivial dynamic programming problem, then you will probably want to use recursive methods to solve it. But I sort of think of the first order approach as being just separate. Just sort of tells you what dynamic programming problem you should be solving, and then you just solve it the best way you can. That's sort of my view. But maybe there's another way of looking at it.